fine.
Okay, do I select got it or leave meeting? I'm teasing.
Good one.
All right, so I didn't leave the meeting, so I'm still here. Okay, so many of you know that I am chapter advisor to the Cradle of Texas. I work for Texas A&M AgriLife Extension and also Texas Sea Grant. And I shamelessly plugged Sea Grant's 50th year anniversary at the state meeting because I think it's a big deal. Let's see. I have been involved with the Master Naturalist program since 1998. I started the Mid-Coast chapter along with the steering committee of individuals, and we graduated our first class in 2000. So I have a long history with the Master Naturalist program. Also was on the state board for several years, and then well, not we, mostly Michelle, and then this other members of the state board. We hosted 2 national meetings to, I guess, for all 50 states to begin Master Naturalist programs. And that was a very successful endeavor because many states have a Master Naturalist program, not all identical to Texas, but the concept's there. So that is that's my history with the Master Naturalist program. I'm a firm believer that training our volunteers and having them give back to educate the people that are living here currently and soon to be moving here, it's important. Y'all are important. All of you are an important resource in helping do that. All right, so tonight's presentation is on aquatic systems and aquatic ecology. So I just combined all those into one title. And while we live on the land, Earth is a water planet. And I think because we're land dwellers, we don't really think about that. But because Earth is a water planet, life has evolved in aquatic systems. And so the aquatic systems on our planet are very diverse. We have marine, we have freshwater, we have still water and flowing water. We have systems that are basic and some that are acidic, and then some that are hot and some that are cold, and even some that are frozen. Oh, let me see here. Okay. All right. So the goals of after this presentation, hopefully, and by the way, this is all from chapter 18 of your curriculum. So I basically lifted that information from there. So, you know, if you don't get the recording right away, you can always read that chapter. But the goals of this, of my presentation, and for what you should be able to do is describe the characteristics of water, should be able to communicate the characteristics and properties of aquatic systems, understand and communicate how aquatic systems function, be familiar with management techniques for aquatic systems, and then understand and communicate threats to our aquatic systems. And that, so let's just start with the basics because that's what the chapter 18 does. This is a diagram of a water molecule. Water is different from most molecules because it's kinky or bent, whereas other compounds are linear. In the center, on the greenish looking circle with the O is the oxygen atom, and then the 2 red circles with the H's are the hydrogen atoms. So the hydrogen atoms do not oppose each other, but instead they form a covalent bond with the oxygen atom by sharing electrons. The angle of 104 degrees gives the water molecule a bipolar structure. And whereas the hydrogen side is slightly positive, has a positively charged, and the oxygen side has a slight negative charge. And so just another diagram to kind of show you that. These are the electrons. You can see that the hydrogen is sharing electrons in this image with the oxygen on both sides. And then it's not a chemical bond or an ionic bond, it's a covalent bond. And that's how those three molecules or three atoms stay together. Well, the bipolar structure also allows individual oxygen molecules to form hydrogen bonds with each other. And when they do that, they form this tetrahedral, which is pyramid in shape. So a different diagram of that would look like that. And then naturally, water would have a whole series of these tetrahedrals, and that would be liquid water. So water has some unique properties. The tetrahedral structure actually gives water its unique properties. These properties include surface tension, specific heat, density, and the ability to dissolve a lot of different substances. Water is also liquid at Earth's moderate temperature. So that's its normal form is liquid. And because of that, it forms oceans, lakes, rivers, streams, and so forth. So our surface water and then even our groundwater. And then water is also stable and does not interact in chemical reactions. It can be part of chemical reactions, but it's not reactive in those. So looking at surface tension, surface tension allows, because of the hydrogen bonds, it allows droplets to form. It allows water to move through tight spaces and living tissues. And then in some cases, it even creates habitat for some living things. So for instance, in this picture, a water strider that is literally has adapted, one of the adaptations of it are its pads on its feet that allow it to actually stand on the surface of the water without sinking. And that's due to the surface tension. And also the surface tension is very strong. And so you may notice, I mean, if you watch swimming events or high diving events, they disrupt the surface of the water with a stream of water to break that surface tension, because it is such a powerful force and not easily broken. And that's all due to the hydrogen bonds. So hydrogen bonds are formed. So looking at water vapor.
And John?
Yes.
There's a question. Hugo, you can interrupt and ask your question, asking about that insect. I think the water strider you were showing.
Yeah, that was my question. Just wondering what kind of animal that was that hangs around on the surface. Water strider?
Yes, a water strider.
Yeah. We're I think you joined a little late, but in John's presentation, he's encouraging people to just go ahead and ask their questions versus using chat.
Oh, okay. Okay.
Yeah, I mean, I don't mind if y'all can, so we can have a more interactive discussion if need be.
Okay.
Okay, so let me see. Shouldn't have put these transitions in here, but anyway, here's some. All of us are familiar with water vapor. Whenever you boil a pot of water, you know, steam comes off of it, and those the hydrogen bonds that are formed that attract water molecules together, it's a weak bond, and so they're easily broken. And they actually form. They form and they break and they reform, and that's going on constantly. So, you know, you might be, you know, we all learned that water boils at 212 degrees Fahrenheit or 100 degrees Celsius. But because of the hydrogen bond, you know, you can have dew on your lawn, and, you know, by midday, it's gone. And that water didn't boil off. It's just that the energy from the sun excited those water molecules, and they separate from each other, and they were lifted up into the sky. And of course, same thing with snow and ice on top of mountains. You know, you have sublimation. So where you're actually getting that state of matter that's where the water is actually frozen, but yet it can still, those hydrogen bonds break, and you actually get some movement of the water back into the water, you know, into the atmosphere. So all that depends on temperature and pressure. And when you have increasing temperature and decreasing and decreasing pressure, that causes increased molecular activity. And that in turn leads to those water molecules breaking free from the surface and forming water vapor. And here again, it doesn't have to be boiling necessarily. It can just be energy imparted to those molecules that cause them to get excited and break free. And then once the vapor cools, then it condenses and forms clouds, going back to liquid water, and then eventually either reforms as liquid water and rain and falls back to earth, or it can, if it's frozen, if it's cold, then it, you know, it becomes ice or sleet. And that's all going on around the entire planet. So another interesting property of water is its density. And let's see, let me flip slides. So water's interesting because in its solid state, it's lighter than its liquid state. And it forms, let me see if I can get this. And it's less dense than the liquid state. So as water cools, it becomes more dense. And this is due to the tetrahedral structure that I mentioned earlier. Water becomes most dense at 39 degrees Fahrenheit or 4 degrees centigrade. As the liquid water continues to be chilled lower than 4 degrees centigrade or that 39 degrees Fahrenheit, it becomes less dense and freezes into, you know, goes to a solid state, ice, at the surface. And that has some implications that we'll see here in a minute. So here's the lattice work, the crystalline lattice work of ice. and it forms that. So you get all these, and if you look at the structures, it's no longer tetrahedral, and that's what makes it less dense. So the ramification of that is that you can have aquatic life surviving under a layer of ice, and it's a relatively constant temperature. So even in the deepest ocean, the temperature down there is 4 degrees, typically 4 degrees Celsius, and it's constant. And so in addition to that, ice and snow make good insulators. And as long as that temperature remains above 32 degrees, then most organisms can survive. Now, seawater, having so much salt in it, it takes a lot more energy to freeze that. But even life that lives in the polar regions, some of the like fish around the Antarctic or Antarctica, they have, well, it would be analogous to antifreeze in their blood, because that water can actually get down below that 32 degrees, but because of the salt water in it, it becomes a slurry. But still, life has adapted to live in those very cold oceans, and multiple ways of doing that. Specific heat. So if we look at heat capacity, that's the amount of heat required to increase an object's temperature by 1 degree. So for instance, a lake would have a higher heat capacity than, say, a puddle of water, because it would require a lot more heat to increase the entire volume of that lake 1 degree. Whereas specific heat is a substance capacity to absorb thermal energy, heat, in relation to temperature at a constant volume. Or another way of saying it simply is to the amount of heat required to increase 1 gram of matter 1 degree Celsius. And actually they measure those, the energy unit is in joules and Kelvin, but we're not in a chemistry class or physical science class, but just be aware that that's how they typically measure units of heat. Of course, we measure calories, right? That's the unit of heat we're familiar with, is calories. So what this means is that water absorbs thermal energy and releases it very slowly. And because the Earth's surface is approximately 75%, it takes a whole heck of a lot of solar energy. A whole heck of a lot of solar energy is stored in our oceans. And we can see that visually when we look at a sea surface temperature of our planet. And so if we look at the purple region, let me see if I can get my pointer going here. Okay, so looking up in this region, this purple region, that's -2 degrees Celsius, this purple color. The blues are going to be in 6.5 to 10.8 degrees Celsius. And then of course you get along the equator, and it's 28.8 degrees Celsius up to 30, where the red is 32 degrees Celsius. So quite a bit warmer, right? So, but the ramification of all that energy stored, we'll see. And just bringing it down home a little bit, here's the Gulf of Mexico. You can see that the browns are very warm water. In this case, the scale is in Fahrenheit. So the very warm areas, like down here around Cuba, around the bottom of the peninsula of Florida, around Louisiana. That's 89, 90 degree water temperature. Here again, sea surface temperature. And then down around the Texas coast is greenish area is about 85 degrees. So you can see that it gets very warm in the Gulf of Mexico. This is actually in August is when this image was taken, August of 2020. But that's just bringing it home to see how, and all of you know, if you go to the beach and get into the water, you can feel how warm it is. So I thought I threw in this slide last year, and this has to do with the change. So here again, sea surface temperature, but this is after one of our hurricanes. I can't remember which one at this time, but you can see how a hurricane passing over the Gulf actually caused the cooler water under the surface to be brought to the surface. And that's what this picture is showing. So you see it's very warm still over in this area, 87 degrees, 86 degrees. But where the hurricane passed through, it's, you know, not freezing, but it's still 2 or 3 degrees cooler sea surface temperatures. And then finally, all that heat that the oceans store, that's what feeds our tropical storms and hurricanes, because they feed off that warm water, and that's what drives the storm system. So it being a water planet, it also drives our weather. So in our case, hurricanes, but then if you look at this schematic, you can see that it also drives our wind patterns and wind circulation around our planet and our oceans. And because of this, it's what keeps what keeps most of our land masses inhabitable, with the exception of our polar regions. But you can see that around the equator, the air, the sea temperatures were warm, and consequently the air above them is warmed, and that it rises. And then as it rises, it gets higher into the atmosphere. Those winds cool off, and then they drop back to the Earth's surface, and you just get that cycle. And so these are what the sailing ships, the sailors of old discovered as they explored our globe. And so you might have heard about the westerlies, and that's what they typically use to move from Europe to the North American continent, or the northeasterly trade winds. So, I mean, if you read anything about history, that's what they didn't know what was causing it necessarily, but they did know that as that warm air rose, and the thing is, as warm air rises, then air, moves in to replace it. And that's what creates not only our wind, but also it creates waves. And then, of course, it does drive our global climate. So that's the importance of specific heat of water and how it affects us. So water is a universal solvent. They call it that because many things can dissolve in water. So one thing that comes to mind, a gas, would be oxygen. So how important is that to aquatic organisms? That oxygen can dissolve in water and then be present for the uptake of that by our aquatic organisms. So if it didn't have the ability to dissolve gases, which would include CO2, but also oxygen, then, we wouldn't have life on Earth necessarily. Well, we wouldn't have life on Earth, or at least life as we know it. Now, 20% of our atmosphere is oxygen, but in the water, and that's in 20% is, 1 in 10, but if you, so it'd be 20 out of 10. But if you start measuring oxygen levels in water, they measure it on a scale of parts per million or milligrams per liter. So it's substantially less oxygen in a water environment than it is on terrestrial environments, which we'll see later can be impactful to aquatic life. Minerals can be dissolved, compounds such as sodium chloride, salt, and all the different salts, and so much more. So water's unique in that regard. I already mentioned that because water is unique, it's a liquid at the moderate temperatures here on Earth. If there was a substantial amount of water on Mars, the extremes, the temperature extremes are so great, greater than on Earth, either on Mars or Venus or Mercury. Water, they don't think water exists on Venus and Mercury, but on Mars, it's in the polar regions, but at some point in Mars's planetary evolution, they think there's liquid water, but that's up to scientists to look at. So we're kind of in a unique spot as far as where the Earth lies, in that water is liquid most of the time, except on our polar regions or on top of mountaintops where it's fairly cold. All right, looking at our planet from space, all of you know it's a water planet, but here again, it's not something that we think about because we live on the land. Water is a foreign environment to us, but the majority of life depends on water and is affected by water. And so if we look at our water budget on the Earth's surface, and about 73 to 75% of the Earth's surface is water. And of that, 97% are oceans, and then about 3% is fresh water. And then if we divvy that up a little bit more and just look at our freshwater budget, we can see that about 69% is stored in our ice caps and glaciers. 30% is groundwater. And then there's a 0.9% of other. And so that part of that other is surface water. So then if we look at our freshwater that's liquid, 87% is in lakes, 11% is in swamps, and then 2% exist in rivers, which is pretty interesting when you think about it. So what's interesting about that is that it's a very small amount of water available for things that live on the land. And that includes organisms that live in aquatic systems as well. So a very small percent of our fresh water sustains, I guess currently 7-something billion people, plus all of our wildlife, terrestrial wildlife, and then all of our aquatic life that's living in freshwater systems, which primarily this presentation is about when we get to that part. So how much, how many cubic miles of water do you think exist in our oceans? Someone want to make a guess?
Would it be like in the billions or trillions?
Yeah, pretty much. It would be in the billions. So because it's such a large number, I'll read it to you. It's 325 billion 520,000 or 833,000 cubic miles of water in our oceans. So that's quite a bit of water. And then even more interesting fact is that only 0.1% of living organisms use less than, sustains living organisms, 0.1%. So it's a very small amount. And not in this particular presentation, but when I give water presentations, I always point out the fact that it's not necessarily a water deficit on our planet. It's a water distribution or delivery problem that we encounter as human beings on our planet. So not all countries have the same ability to have that water.
Hey, John?
Yes.
Hey, I wanted to ask a question. Is there some interchange between the saltwater and the freshwater?
Is there what now?
Some interchange? I mean, some of the saltwater, evaporating and becoming, maybe that's what this chart is about here.
Yeah, absolutely. And so this is a diagram or a screenshot I pulled off the United States Geological Survey. And if you were to find this on the internet, and I was considering actually bringing this up and switching screens and showing it to you, but this is a water cycle. So there is no new water on our planet. All the water we have here was, I guess one theory is that it was brought here via comets crashing into our planet during the 4.5 billion year history of Earth. And so it changed the face of our planet because at one time Earth was just a molten ball of lava. And then the water came, and here again, they think it's from comets crashing into the planet. And then over time, our planet actually became covered with water. The continents actually, formed. Then we went through a series of freezing and thawing and freezing and thawing several times throughout our billion-year history of the planet. And then here we are in modern times. And so all the water we have is the water that has existed, and everything, all the water is recycled. So the water cycle or hydrologic cycle is how water passes or is reused in the environment. So we can start anywhere on this chart, but to me, it's a natural because of my bias towards oceans and salt water. We'll start out here with the oceans. Once again, the sun's energy, that's what drives the entire system. It warms up the surface, the ocean sea surface. Those water molecules get excited. They start bouncing around. They start breaking free, and then they rise up, and they form clouds through condensation. And then, of course, we have an atmosphere, so they don't go flying off into space, right? Now, I guess we do lose some water into space, but it's a very small amount that happens. But anyway, so it forms clouds, and as those clouds move over say, mountain ranges, then, here again, it's colder. It might be minus 54 degrees Fahrenheit on top of, Mount Everest, for instance, so that, you form snow, it freezes, falls back to Earth, either becomes locked up in ice sheets or glaciers or snow caps. And then, but eventually you get some of that snow melting, and then you get that runoff that flows down into rivers. And then that water then makes its way to the lowest point through a series of rivers, creeks, and streams, and then eventually winds back up in the ocean to start that part of the cycle. It also, of course, comes down as rain, liquid water, precipitation. But then you get trees or cows or people, we consume the water and we excrete it. Plants release water through their leaf system, through the leaves. That's called evapotranspiration or transpiration. And then some of that water actually goes under the ground and then recharges our aquifers and that are stored water underground. And then, of course, we can extract that water through a well system. The other thing, too, that this doesn't really show, but, well, I guess it does here on the lakes. You can see the seepage. So you actually have water movement through the banks of the rivers, and it can actually seep and go back into groundwater. And then, of course, on this lake, they're showing some seepage back into the groundwater systems. But here on the coast are estuaries, which you'll be learning about in another lesson in a little bit. Our estuaries have brackish water, which is fresh water from runoff from our bayous or from the land. And then that water then mixes with seawater from the oceans, and you get brackish water. So brackish water is defined as 6 to 20 parts per thousand salinity. And that's all salts, just not sodium chloride. Sodium chloride is the majority of the salinity, or the majority of the salt that makes up the saltiness of the oceans, but it could be, there's other salts involved too in various levels, but sodium chloride is the highest concentration. Whereas full strength seawater is defined as 33 to 35 parts per thousand. So a part per thousand, is grams per liter. So if you think, so I guess about 1 gram there's about 28 grams in an ounce. So if you want to think about that. So if you had 1 liter of water that had 28 grams in it, that would be, your 28 parts per thousand. So anyway, that's a little bit, but all that water is recycled. And kind of an interesting factoid is that, I don't know who did the study, but I've read that before water reaches the coast, that it passes through at least 11 to 13 people before it reaches the coast. And, if you think about it, that makes sense. So people are drinking water, and then they're eliminating it. And then that water can re-enter the water cycle and can come down, and then another person drinks it, and so forth and so on. So, but that's our water cycle. So yes, fresh water does interact with seawater. In some very severe cases, you can have saltwater intrusion, and that's one of the threats, jumping ahead, but that's one of the threats to like the Columbia bottomlands. So the thought is, as we remove groundwater from the Gulf Coast aquifer, that allows salt water to intrude, to move further inland, because there's no hydrostatic pressure keeping it back. So it allows it to move in. And when I worked in Louisiana, when they dug the Mississippi River Gulf outlet, which was a shipping channel, right, cut right through the land. If you think about the Suez Canal as an analogy, that allowed seawater to infiltrate Cypress Tupelo swamp and just killed the entire freshwater system. So, you know, we do have the ability, man has the ability to affect our aquatic systems quite a bit. Any questions on that? Water cycle, you know, is something that students learn in the third grade, typically third and fourth grade. But every bit of water on Earth is what we have, and short of some catastrophic event, we're not getting any more. So switching gears to a watershed, because it goes directly back to our hydrologic cycle, or the water cycle. The simplest definition of a watershed is that it's a geographical area that drains into a common water course. And so a river basin is also a watershed. Watersheds are not limited by size. A watershed can be as large as the Mississippi River Basin, which drains 2/3 of the United States, or it could be your front lawn. So it's not size specific. And if you ever go out, say for instance, into your neighborhood, and after a rain, you know, you'll see the water flowing off the lawns into the street, and then flowing along the street into the storm drain, if you happen to have storm drains in your neighborhood. And then, you know, that water then goes through a series of pipes under the ground into a bar ditch, and the bar ditch, you know, takes that water either to a natural water course, or maybe, depending on how close you are to the coast, directly into the bay or to the Gulf of Mexico. So anyway, this is a watershed, and you can see that you have some topography to it. So this is higher on the sides, so that funnels the water down towards the central water course, and then it flows downhill. And so you can have forest, you can have urban areas, you can have farmland, you can have industry, suburbia, wetlands, so forth and so on. Some of that water does, of course, interact with groundwater. The surface water does interact with groundwater. Can interact with groundwater. So, typical
I have a
water.
question.
Yes.
Okay, I'm wondering two things.
Okay.
So given the runoff and, you know, fertilizers or whatnot that run off into that, and let's say that goes down the watershed and it goes into the main, like, so you have it flowing down, you know, all the channels that lead to the open water, right? So you have fresh water to start with, and then it has all the impurities and all of the whatever's, you know, draining off everybody's yard. And when that enters into the ocean, like, or into the main, you know, big body of water, does it just, I mean, I know we got 75% of the world is covered in water, but it just seems like the concentration of that kind of stuff, does it settle to the bottom? The impurities, do they settle to the bottom and just become part of the ocean floor? Do they dissipate? Do they, you know, fill our waters? Do you know what I'm saying?
Yes. And so I guess it would depend on what the impurities are, right? So
Well, let's say fertilizer, just for instance,
okay.
fertilizer.
So fertilizer, for instance. And by the way, all of you should receive an annual water report from your from your municipality, unless you're out in a rural area and are on a well, in which case I would highly recommend that you get that water tested annually. But it's going to list those impurities in your water. And one of the ones that I commonly see in these water reports, and a lot of times now they may not be mailing them, they may be just posting them on their city website. So check out your city website. But one of them is atrazine, which is found in pesticides at varying levels. So, but to answer your question, if we talk about fertilizers, those excess nutrients, and this is more about threats to it's, first of all these items that we're talking about, pesticides, fertilizers, household hazardous chemicals, used motor oil, used antifreeze, whatever people are putting out on the land and impacting the water, our water, that's all considered non-point source pollution. And it makes up, I believe it's 78 or 80% of all pollution. So the other pollution, point source pollution, is regulated. It's permitted. So if I'm a industrial plant and I'm discharging into the environment, I have to go to EPA or Texas Commission on Environmental Quality and apply for a permit to discharge. And then if I exceed my permitted amount, then I get fined. So it's all regulated. But it shouldn't be any surprise that these other sources of pollution, the non-point, which all comes from all of us, is not regulated. So the only way we can regulate it is through education and awareness, right? Increasing public awareness. But to answer your question, many years ago, the big concern was nutrient pollution. And that was coming from excess fertilizers. And in fact, further on in my presentation, that's also what's driving the hypoxic zone in the Gulf of Mexico. So the microscopic plants, the algae, they thrive on that fertilizer, right? And so that system can become very enriched. And so we call that eutrophication. And it all, looks, depending on how dense that algae bloom is and how long it lasts, can be a detriment to aquatic systems. If we look at red tide, Florida has a persistent red tide on the West Coast. And I'm hoping that at our November general meeting, we're going to have someone come talk about harmful algal blooms. Maybe the science is changing. It used to be red tides were driven by salinity. So if you had high salinities, the red tide organism is always present. But with high salinities, it can bloom. But what I'm interested in knowing is, are fertilizers spurring that growth? Because red tide is a dinoflagellate. It's not an algae. It's one of those unique organisms that's a plant / animal. And I suspect that's what's driving the persistent red tides in Florida is fertilizer runoff into the Gulf. But then we had a brown tide in the Laguna Madre, which persisted for a number of years. And I believe that was, was an algae, and it was driven by fertilizers. So Does that answer your question?
Yeah.
A system in balance typically won't have the excess nutrients to cause these blooms. Have any of y'all been to Resolve Park?
Yes.
Yes. What
Yeah.
color is that? What color is that water?
Brown.
Brown.
Green.
Not when I was there. But anyway, we'll talk about that a little bit further on. But as far as pesticides and things, well, I mean, they're poisons, right? So they can affect aquatic systems. In fact, there are some, they talk about indicator species. So some aquatic invertebrates can't tolerate any pollution, any impact, degradation to the water, or they end up dying. But great question. What was your second question? Or was that it?
Let me see, am I unmuted?
Yes, you are.
Yes, okay. Well, the other one is just a simple curiosity because I like to fish. So the brackish water, so you have fresh water coming in that's going to have a different kind. And they talked a little bit about this at another one of the field trips we went on. So you have like fresh water, and then you have brackish water, and then you have salt water. Is that kind of the progression of things? So
Yes.
you don't have So what happens when you have heavy rains, then the fish that are usually out there that you go catch, do they just go out? I guess they just go out to deeper water, and then you get a different subset of fish when you go fishing, or you know what I'm saying?
Well,
different.
actually, a lot of our fish that are in our bay systems have adapted. We call them euryhaline.
Euryhaline.
Yeah, it's a new word for y'all. But euryhaline means that they can tolerate a wide range of salinities. Everything from 0 up to 40 to 50 parts per thousand.
Mm-hmm.
So that's why you can have red drum or redfish, it living in freshwater lakes. And they actually grow quite nicely, but it's fresh water. But they're euryhaline, as opposed to what they call stenohaline, which is a narrow range of salinity.
Can you spell haline? Haline?
Haline.
Haline.
Okay. And you'll probably get that in ichthyology when y'all have that.
Okay. Thank you.
But so yes, I mean, if it's a fish that can't tolerate that change in salinity, they will actively move to an area where their salinity tolerance is better. I mean, fish, it's pretty amazing. I mean, fish will seek out higher oxygen levels. They'll seek out higher salinity levels if that's what they need. Mm-hmm. And then, of course, once they're and it all the feedback mechanism has to do with, well, obviously, if there's not enough oxygen in the water, they can't breathe, so they need to go find some oxygen. But as far as the salinity levels, their feedback mechanism and their osmoregulation changes, right? So they're adapted to live in that aquatic environment. And so they'll go find they can't tolerate, some fish can't tolerate living in freshwater for an extended period of time. So they'll move further out to where they find salinity. And then that feedback then is a more efficient way to osmoregulate, which is balancing the salts in their bodies versus externally. And then that's how they go about it. So if you're an organism that can't move, like oysters in our bay systems, then if the water hangs around, fresh water hangs around for a very long time, it can basically decimate the oyster reef and kill it off because they can't. They'll seal themselves shut and not filter feed. But if it's a persistent flood and remains there, then that reef and organisms that can't move out readily will succumb to the fresh water.
Thank you.
Good question.
John,
Yes.
you brought up Resoft Park, and that is our project, our group project this year. Would it be possible that you could stay on a few minutes after you give us the lecture and just discuss with us what you know about that?
Well, so who's speaking?
Pat Jeffries.
Okay. So Pat, I suspect I've measured, and when we get further into water quality about for aquatic systems, I measured the relative clarity of that water at one time, and it was, I guess, 8 or 10 inches visibility from the surface that you could see down, and that remains pretty constant. And I think they have bubblers out there now. The county has put bubblers to help with oxygenate the water, or aerate the water, not oxygenate. Add oxygen to it.
What are bubblers?
Well, it's a system where they have a low pressure, high volume blower, an air pump basically, and they're forcing air through water lines, and then the bubbler is something they either suspend mid water column or put on the bottom depending on the depth, and then it bubbles, it aerates. That's a bubbler. It's an aeration system.
Oh, thank you.
And then if you go out there, you'll see it. But I suspect with being, it's not uncommon to find aquatic systems that are being impacted by runoff from neighborhoods. And I suspect that's what's going on with Resoft Park. The other source of nutrient runoff in, well, just not Brazoria County, but other counties are, failing or old septic systems that have failed and need to be upgraded to the newer systems. But that's a whole nother topic. But that does input bacteria. So the fecal coliform and the coliform bacteria, and then it also creates excess nutrients that then impact our water bodies. But that's all over the coast. So on this particular slide characterizing aquatic systems, aquatic systems are broadly divided into 2 different types. You have the lentic or lodic system. If an aquatic system is lentic, the water is standing. So that would be a lake would be an example, a lake or pond. If it's lodic, it means the water is flowing. Obviously, examples of that would include rivers, creeks, streams, etc. You can have both lentic and lodic characteristics associated with a common system. So if you think about a lake, or think about a reservoir that's not a natural lake, that a body of water that's been impounded, where they've dammed the river, you have the lentic and the lodic combined, right? So the river is going to be your flowing water, your lodic part of that aquatic system, and then it flows into the lentic system, which is the standing body of water. And we'll get into some of the specifics about each one of those. So our lodic systems, here again, are going to be creek, streams, and rivers. Before I get too far, just be aware that there's a classification of rivers, creeks, and streams. And so all the streams in a watershed are classified based on size and number of tributaries. So this is how they do it. So the smallest streams with no tributaries are first order streams. And then when two first order streams, say for instance here, there's no tributary. So this would be the headwaters, this would be the headwaters. As water flows down a first order stream, and we have two, and then they converge, that creates a second order stream. And this is how all flowing water or channels of water are classified. And the classification goes from first order up to 10th order. But in this diagram, you have two second order streams flowing together to make a third order. When it comes down and you have a first order stream flowing into a third order, you can see that it does not change the order, right? Because the first order has no tributaries, but then as we continue downward, you see two third orders come together, and that makes a fourth order. And then here again, you have a first order flowing into a fourth order, and it does not change it to a fifth order. So they have to be of equal size, and they have hydrologists that go out and measure, oh gosh, flow volume. There's characteristics that they use to do that, but it's based on, well, whether it has a tributary or not, but then it also goes into how much volume that channel is carrying. And so they'll go out and measure those. First, second, and third orders are considered headwater streams. A fourth through sixth order is considered mid-sized streams. And then a 7th through 10th are known as large streams or rivers. So just be aware that we classify our creeks, rivers, and streams in these orders. If we look at this diagram, these are the major bay systems and river basins in Texas. So over here, we have the Brazos River Basin, which is going to be running along here. Just to give you some orientation, here's the Brazos, Colorado coastal basin. That's going to be this one here. Let's see, looking at the Trinity, for instance. So we have the Natchez, well, sorry. Trinity River Basin down here, and it's pertinent because they talked about the Trinity River during the state meeting, but you can see that it starts up here in the northern Texas and flows down into Galveston Bay. So these maps are available on Texas Parks and Wildlife's website. You can also get them from the Water Development Board, Texas Water Development Board, and a whole variety of other places. But I pulled this from Texas Parks and Wildlife. And then it also gives our major bay systems as well. All right. So I pulled this chart right from the book, from y'all's curriculum, just to give you an example. So the Brazos River, the length of it in Texas is 840 miles. And then this is what these hydrologists do, right? They go out and measure surface area of the the surface area, the flow rates, the volume, and so forth and so on. But you can see that the Brazos River has 19 reservoirs on it. And acre feet, if you, this is storage capacity of those reservoirs combined, 75 acre feet per square mile. So an acre foot, if you think about it, is 1 square acre covered with 1 foot of water. That's how they typically measure volume of water in a large system. And then just some other examples, some of the other major rivers here in the state of Texas to give you some reference. So here's the Rio Grande. Someone asked me I guess in a previous presentation I did concerning this, what order is the Brazos River? Because that's the one that we should all be familiar with since it flows right through Brazoria County. I looked it up. It's an 8th order river. So it's definitely a major river. But I think what's interesting is just looking at all these different reservoirs that have been constructed. So we've put a lot of dams on our rivers, and there's a consequence to damming a river. It holds back the sediment that replenishes our marshes. And that's one reason why Louisiana is washing away, because the sediment that comes down the Mississippi River, which I'll just jump to the next slide. So here's river basins of the United States. This is the Mississippi River Basin, draining approximately 2/3 of the nation. Of course, you have, the Ohio River over here, and the Mississippi River. Actually, the headwaters are up in Minnesota, but it drains a substantial amount of our country. And the sediment load, and you've all seen the Brazos, it's a red clay, and it flows directly into the Gulf of Mexico. So that's why you have all those, a lot of times you have that heavy layer of red clay under the sand where you find some erosion. I'm thinking primarily like Sargent Beach, because that's the predominant direction the currents flow is from east to or from the north to the south this way. So it deposits a lot of clay along the coastline. But all the sediment is flowing out to the Gulf of Mexico, and off the coast of Louisiana here, it can be 1,200 feet of water or more. And consequently, because they've levied the river to protect New Orleans, well, I mean, literally it's almost levied from the entire length, since it is a major navigable river. That sediment load is not being deposited back onto the land, and the impact for Louisiana is that it's causing the state to wash away, because it's not being, they're not getting any accretion, any land buildup. But all our rivers are dammed here in the state. Some of them have multiple water control structures, and it just cuts off. It just cuts off that sediment load from reaching the marshes here along the coastline. And consequently, part of that is that going back to, I think it was Angela talking about non-point source pollution. As all our reservoirs over time, they fill in, right? Because that sediment flows down, it settles out, it begins to fill up. That's the natural progression. You might say, well, why can't they? So a lot of our reservoirs have lost capacity to store water. And you might say, well, why can't we go in there and dredge them? And you could, it's very expensive to dredge them. But what they're finding out is that that sediment is contaminated with all sorts of heavy metals or sources of contamination. So to go in there and dredge it would be resuspending all of that. And so that's not an easy solution. You just can't go in and dredge a reservoir out for multiple reasons. All right. So looking at some of these stream characteristics, generally streams inland have a steeper gradient, therefore faster flowing water. They tend to be rockier, and the water tends to be cooler than streams on the coastal plain. And also they tend to be clearer, right? Because there's less sediment. A mountain stream, say up in the hill country, you might have boulders. You'd have, you'll have gravel beds. So, I mean, if you ever go to the hill country and look at some of the rivers up there, you can see the major difference between the river in the hill country versus the same river here along the coast. Those rivers are also tend to be narrower, and like I said, they flow faster. Whereas when they reach the coast where it's flatter, they tend to those rivers tend to get wider and carry a lot more sediment load with them. Unfortunately, I apologize. I changed my design format of my slides and it caused my pictures to move. But so a perennial stream has a constant flow, whereas an intermittent stream, they flow occasionally, and they're usually first or second order streams. So if we take a look at that, here's an intermittent stream where some times of the year they can be dry, other times of the year they can be flowing, or maybe right after a rainfall, they're flowing, but then they stop flowing. And so one of the presentations I attended up in at the state meeting was about karst, which is limestone systems. And they talked about on a lot of these rivers up in the hill country, it's a sinkhole. So the runoff just drops from the riverbed directly and goes directly underground into the aquifer. And so you can, once that happens, all the volume of that river channel can go into groundwater, and then beyond that, it's a dry riverbed. Sometimes that river comes back up to the surface as an artesian spring, and then that river will pick up and keep flowing. But so you have perennial streams and then intermittent streams. Let's see, and then just here's some examples. So this is going to be out in the western part of the United States, but you can see it's dry here, but then you get this seepage coming up out of the sediment here, and then that water picks up and continues to flow downstream. And then another picture, just to give you more reference, this is one I took in Alaska, and you can see the snow back here, but you can see that it's dry back here, but the water's flowing under this gravel and rubble, and then picks up and begins to flow into the main channel here, and then continues on wherever it's going. All right. How are we on time for break? I've been at it for about an hour and 15 minutes thereabouts. Are y'all good, or y'all want me to keep going?
I'm okay.
I'm
Good.
good.
Okay.
Yeah, I'm good.
Okay. Just checking. All right. So what are some of the characteristics of our loading systems, our flowing systems? Well, as I said earlier, that these systems vary greatly in flow rates or velocity of water. And that's largely dependent on the slope or the gradient. It also depends on whether there's rainfall or snow melt or some other source of inflow upstream. And it can also, upstream in the area. These streams with the high flow rate or velocity can erode stream beds. I haven't ever made it out there to see it, but this is not quite off topic, but it's called Government Gorge. It was, I forget when it was formed, but at Canyon Lake, there was so much rain at one point that they could not release enough water through the spillway. And so the water in Canyon Lake started going out the emergency spillway, which is there to keep the dam from blowing, right? Because, I mean, if the dam let loose, goodbye New Braunfels. But consequently, in that short period of time, that water, the force of the water eroded through the limestone bedrock and created this gorge, which I believe is 100 feet deep. And so there's some pretty impressive photographs of that that was created just by the force of water. And so water can erode in a very short amount of time bedrock. Typically it's slower, and it does depend on the type of rock, but it does have the capacity to be very destructive depending on the flow rate and the velocity. Water can lift up and move boulders, stones, gravel, sand, and silt. That moves it all downstream. So like I said, if you go up into the hill country towards headwaters, if you find headwaters of a creek or river, you might find some very large rocks or boulders in the middle of the stream bed. But then the further you go downstream, the particulate size of that sediment gets smaller and smaller until you get into the sand and silt. And so that's what we get typically down here at the coast. Water also moves nutrients, sediments. It can dislodge aquatic organisms, which include aquatic invertebrates and vertebrates. And all these animals have adapted to survive in moving water. And here again, it depends on how fast that flow rate is. If they lose their footing, so to speak, then they get washed downstream, or they end up being food for hungry fish waiting for it to come. So in this diagram, streams are characterized by either a pool, so the water's flowing this direction. So you have a pooling effect. And then right here, you have a change in the stream bed where it becomes a riffle. So it goes from a deep water to very shallow water. And then these are called riffles, and then you get down here, these could be rapids, but that repeats itself going down the river channel or the stream channel until it gets to a flatter terrain. So you get this repeating itself. So let's take a little look at that. with some more descriptive stuff in it. So let's see.
One time I seen on TV, they had this where they built like a road over this creek or something, and all these salmon were running up over the road to try and get back where they needed to go. Would that be part of like what is going on right now?
Well, you know, they put here again, you know, with salmon, we realized that by putting dams on the rivers, that has impacted the Pacific salmon. And so one of the media attempts to mitigate dams was to put fish ladders, which allow the salmon returning from the sea to spawn to navigate upstream. So it could be an elevation of 20 feet, right? So these fish just can't jump that high. It's amazing how high they can jump, but some of those changes in elevation are too great and they can't jump. So they have fish ladders, which divert some of the lake water down this ladder, and the fish use that to move upstream. Well, now that's because the Pacific salmon, the 5 different species that live in the Pacific, are, I wouldn't say they're threatened at this point, but it is a huge consideration because they are reduced in numbers, that they have now started removing some of these dams or structures from the rivers to completely and allowing it to free flow like it used to. So
thank you. That was very interesting.
Yeah, here again, and it's amazing that the fact that these fish, you know, they return right to spawn where they were hatched to the same river, but it's amazing that they can swim through literally inches of water and just make their way upstream. I mean, of course, they die after they spawn, but it's very interesting once they lay their eggs. So here's another picture. This is one I took in the hill country just to give you some point of reference. This is on the Lampasas River, but I think this is taken from a bridge that crosses the river, but I think it gives you a good perspective of what I was talking about in the previous slide. So you have this deep area, a pool, and this pool is formed by the erosion from water eroding along this segment of the river channel. And that's what deepens it, right? And if you look right across, you see the point bar. So up here, you get some erosion happening. And what's eroded, and I'll talk about this in the next slide, the material that's eroded from this bank happens because the velocity of the water is faster along this outer bank. And so it erodes that material. In this case, it's limestone and probably sand and gravel. And then it gets past here, and then the velocity of water slows down, and it kind of almost ricochets like a ball on a pool table from one side to the next. So the water hits this bank, erodes it, bounces off, slows down, and then drops out that heavier sediment to this side of the bank, which then forms this point bar, which is actually the material being deposited. And then of course, here's your riffle. And then this is called a run. So this is a free flowing area where the water just flows uninhibited. You don't have an erosional zone. You don't have a pool. Although further upstream, you can see a point bar here. You can see a big point bar here. So the erosional zone is probably on this side of the stream channel. And then of course, this is the floodplain, right? So this elevation on this land is higher. So it's definitely probably 6, 7, 8, maybe 8 feet above the surface. Whereas this side is eroded, and you can see it begin to creep upward in elevation, but this would be a floodplain. So if this water ran out of this channel, it would, as it began to fill up, this is the relief valve. The water would flow out across the land and spread out, and it wouldn't be all flowing downhill in a raging torrent. So that's Mother Nature's way of dealing with floods. Let's see. But like I said, that's hill country, so you have actual rock and not just deposited silt and clay that you find down here. So meanders, which these are all meanders, or they're bends in a stream or river channel, and all stream and river channels, even drainage ditches, you can even see meanders form in a drainage ditch. But this is a really good photograph, an aerial view of it to show y'all. But the meanders are here again. You get this erosion. So along this bank here can be very deep, and it's cutting. And then you get this depositing over here. And then sometimes a meander, depending on, say you have a catastrophic flood, you could have the water actually cutting across this land here and basically going directly, instead of making this bend here, it just cuts straight across and changes course. So if you look at Google Earth, if you have that, I would encourage y'all to look at Google Earth, because you can, Oyster Creek is ancient river channel of the Brazos River. And if you look at Google Earth at, say, the Mississippi River, down towards the coast, you can actually see the old river channels that were formed over the thousands of years. And if I'm not mistaken, the Mississippi River has changed course something like 7 times over to modern times. And it almost changed course about 10 years ago when there's a big flood on the river. And it wanted to go down into the Atchafalaya River, but they have a water control structure there, and it almost blew out that water control structure. Had that happened, New Orleans would have had a problem with their port. But anyway, these are meanders, and it's Mother Nature's way of slowing down the flow of water in a river channel. All right, switching gears to lentic systems. These are our stationary bodies of water. They're non-moving, but you know, water's always moving, either through currents or wind or whatever. So, I mean, when I say moving, I mean they're not flowing like in a river channel. Lentic systems receive water during and after rainfall events, and they can overflow the banks. So I've actually, having been from San Antonio, and I've talked about Canyon Lake, and I'm sure there's other lakes, I've actually seen all the recreation and picnic areas flooded. So when the water came down the Guadalupe River, it overfilled Canyon Lake, and here again, they couldn't release the water through the spillway fast enough, because, you know, they got to consider downstream towns and municipalities. And consequently, that water backed up in the lake and ended up flooding around the perimeter of the lake. So it was never intended to flood those areas, but it did. So you can have systems reach their capacity, lentic systems reach their capacity and cause localized flooding around them. lentic systems do tend to be more productive than lotic systems. And this is due to the sediment and nutrient accumulation that flows in. So here again in Texas, our lakes are reservoirs, and it's because we have them because we put a dam on the river. And all ponds and lakes will gradually fill up, and they'll eventually become a bog or a wetland. And that's just the natural succession of a lake, is that they do silt in. Takes years for that to happen, but it does happen. And it is part of nature's successional cycle, and that in fact, Caddo Lake, our only natural lake in Texas, or Caddo Lake is our only natural lake in Texas, and that was actually all the other ones are man-made because they've dammed them. And then many of our lakes, and I talked about this earlier, but many of our lakes have reduced storage capacity because they're filling in with sediment. And then if we look at a couple of different types of systems, this could be, minus the nice hill here, this could be in East Texas with the piney woods or the trees. But this slide is probably not from Texas. And then, but that would be a lentic system, a nice pretty lake. And then here's one to give you a contrast. So here's one that's more bog-like or a freshwater wetland. But clearly it's not a deep lake like in that previous picture. So it is filling in over time. And then you even have these systems, these ephemeral ponds. And in this, they tend to occur in desert regions or up in the plain states where there are depressions in the landscape. And when it rains, they fill up, and all life in these are adapted to literally take advantage of the few days that water's there. So they hatch, they reproduce, they lay eggs. I mean, they lay their eggs, and then the pond by that time is dried up, and then they disappear, and then the eggs are what's left for the next rainfall. But so these are just a different type of lentic system. So when we look at lentic systems, this is a very, they have different zones. And so everything from where the terrestrial plants end, and if you have a pond or when you all go to Resolve Park, there might be, I'm trying to think if there's a decent area there where you can actually see the transition from terrestrial plants to aquatic plants. But everything from the emergent aquatic plants out to where the water becomes so deep that you can't, that the submerged plants aren't able to grow any further, is considered the littoral zone. And then when you get out into open water, that's called the limnetic zone. This euphotic zone is where you have sunlight penetration. And then when you get into very deep lakes where you don't get a lot of sunlight penetration, that can, you know, the zone along the bottom is called the benthic zone. But then what's interesting about deep water lakes, or almost any pond, and we'll get to it here in a minute, is that they do stratify. And so we'll talk a little bit about that. So that's just a diagram to show y'all how the different zones that are out there. And then here's another one where we can talk about the stratification that sets up. So up in the epilimnion up here, that's where you get maximum sunlight, so you have the highest productivity. You get maximum mixing, so there's no stratification from the surface down to this thermocline. Water temperatures tend to be higher, and you have a higher dissolved oxygen level. And that's just not from mixing, but that's also oxygen that's coming from plant respiration. So when you have a bunch of microscopic algae, microscopic plants, phytoplankton producing oxygen as a byproduct of respiration, then that does maintain high oxygen levels in this epilimnion. As you go down, you hit a thermocline, which is a temperature barrier. And if you've ever gone swimming, you've probably have felt that. Yeah, has anyone ever felt the thermocline in a lake?
Yeah.
Yes.
Yes, I
Okay.
have.
Yeah, so it's very evident when you hit it, right? So as a scuba diver, you actually just punch through it. It can be very narrow, the band, or it could be, could be 10 feet band of cold water, but you definitely know it when you hit it. Then you get to the metalimnion, where you have limited sunlight. So now we're getting deeper, and you have lower productivity. And then there's a rapid decline in water temperature. And then you can even have this in very deep lakes. You can have the chemocline. Now we're getting the very deep lakes that have no sunlight penetration. Therefore, you don't get any primary productivity. It's stratified. You don't get mixing. You have low dissolved oxygen and very low temperatures. So if you think about the Great Lakes or Lake Baikal in Russia, which is over a mile deep, this is that area, right? So, I mean, that's super deep, and you're just not, and really sunlight only penetrates about, where it can, well, it's just not sunlight. It's also pressure. So for every 33 feet, you're adding an atmosphere of pressure on top. But primarily the sunlight rapidly attenuates and then disappears, and you don't have plant life below that. And then of course, in oceans and lakes, you'll have the phytoplankton and the zooplankton dying off, and then it rains as a snow, if you will, a biological snow. So all lymphatic systems turn over, and it has to do with one of those properties of water. So remember I said about density. So if we look at our diagram here in winter, it's 0 degrees or 32 degrees Fahrenheit, 0 degrees Celsius. But if you look at our graph down here, it's 4 degrees. So where's the most dense water? It's going to be in this 4-degree range, right? Because water is most dense at 4 degrees Celsius. So it's sunk. Well, when the springtime comes and the water temperatures, the surface water begins to warm, it goes from 0 degrees to warms up to 4 degrees Celsius or 39 degrees Fahrenheit. And then this water becomes dense, denser than the water underneath it, and it begins to sink. And as it sinks, it displaces the water underneath it and pushes it up. And that's your first turnover. And a spring turnover is what they call that. Summertime rolls around, you get the summer stratification. So here again, your densest water is at the bottom. It's very cold. It's low in oxygen, where you have your water, warmer water temperature floating on top, because, you know, warm water is less dense than the super cold water down here. This is your summer stratification. And then when fall rolls around, the surface water begins to chill. It becomes to get denser and denser, begins to sink. And then here again, it displaces that water and you get a fall turnover. A lot of times you can tell a lake has turned over. Even farm ponds that are very deep will turn over. I don't know about Resoft Lake. It's probably not that deep. It's got to stratify first in order for it to be able to turn over. But that's the natural cycle of nature. Now, in smaller lentic systems or ponds, you can have turnover due to wind events or thunderstorm events where it rains a lot of cold rain, and that actually can cause a pond to turn over. A small pond, it's probably not going to have a lake. It's probably not going to turn over a lake. Any questions on that? Looking at the next slide, we have our plankton, and I just lumped everyone in together: phytoplankton and zooplankton. So the phytoplankton are the greens things, which are the plants, the microscopic algae, diatoms, which are some of them. Most of them are photosynthetic or photosynthesized, but you have all your microscopic algae, which then support the zooplankton, which are the animals. So we have a Daphnia, we have a mite, we have rotifers, we have a hydro, et cetera, right? And just another picture of a bunch of zooplankton in a jar. Looks like pepper. And then when you zoom in and get closer, they're actually little insects or crustaceans. So you have copepods, you have Daphnia, etc. The next type of animal we encounter in lentic systems and also lotic systems are what they call neuston. And that's kind of a new name. Well, it hasn't, as I don't think where I was using it back when I was in college, but it's the acceptable name nowadays. But those are going to include your larger invertebrates. By the way, plankton, the word plankton basically means that the animal is at the mercy of the currents. So they don't swim. They're not strong swimmers. The neuston are okay swimming, but they don't swim a lot. Right? So looking at some of the other ones, we have some dragonfly nymph, we have mayfly, we have damselflies, and if you didn't know this, are terrestrial dragonflies and damselflies all start off as an aquatic larvae or nymph is what they call them. And just not dragonflies and damselflies, crane flies, mayflies, stoneflies, black flies, etc. They all start off in the water. So the adults lay their eggs in the water and they hatch out. All right, I'm losing my cursor here. For some reason, does not like that. And then you have nekton, which are the strong swimmers, which include the fishes. And primarily we're talking about freshwater fishes. but nectin can also be saltwater fishes as well. And so if we look at our aquatic food pyramid, we can see that the primary productivity or the primary producers are down here. And while the Amazon rainforest is important for biodiversity on our planet, all these algae in our surface water, including our oceans and marshes, are the primary oxygen producers on the planet. Obviously, terrestrial plants produce oxygen as well, but the majority of oxygen comes from our aquatic systems. But you don't only have your phytoplankton, you have your submerged vegetation, and then you have your emergent vegetation, your cattails. And these sustain a whole variety of animals. So they sustain it's the zooplankton that are feeding on the phytoplankton. And then you get some of these larger critters. The snails are grazing on algae that is growing on substrate. The caddisflies they tend to live in moving water, and they make a case out of either shell, twigs, a variety of things, actually spin a web and glue all that together. And so it's almost like a hermit crab, if you will, except hermit crabs don't make their own home, but a caddisfly gathers the materials and builds its home. And they actually are, I guess, filter feeders in that they'll actually, because of their silk, they can spin a web and they catch fine debris that's being washed downstream. Then you have your tadpoles and you have a whole variety of insects. So the dragonfly nymphs are predatory, but then you get a lot of invertebrates that are feeding off some of that detritus, which is decomposing plant material. But there are some of those animals that are aquatic insects that are predatory, and so they'll feed off living things. And then you move up the food chain or the food pyramid to, the larger or the medium-sized fish, in this case, a green sunfish, and then that becomes prey for the largemouth bass. And then eventually your apex predator in our system is a great blue heron, and it's going to eat pretty much whatever it can catch: snakes, largemouth bass, small fish, frogs, so on and so forth. Of course, what you'll also notice is at the entire time, you get an energy loss out of the system. So there is no 100% transfer of energy from one trophic level to the next. And these are called trophic levels. So you have your primary producers, primary consumers, secondary consumers, tertiary consumers, and so forth. And then after everything dies and re-enters the system, you have your decomposers, which of course break that down and recycle all that material. And if you want to get philosophical about it, it's all the sun's energy that's driving all that. So every time you eat, you're eating sun's energy. Let's see the next slide I have is just to show y'all that it's the 10% rule. So in theory, about 10% of the sun's energy makes it to Earth. And then that energy spurs the primary productivity for the plants to photosynthesize. But here again, at every level, trophic level going up, only about 10% of that energy is transferred upward, and then the rest is used up for growth, maintenance, reproduction, respiration, osmoregulation. So what does that mean as far as in a system? Let's say if you wanted a 10-pound bass, a 10-pound bass would eat, or let's say a 1-pound bass would have to eat 10 pounds of fish. These fish would have to eat 100 pounds of invertebrates, and these invertebrates would have to eat 1,000 pounds of plant matter. To put that in perspective. All right. I've got about less than 20 slides. We can keep pushing forward or take a break. It's totally up to y'all.
Let's
I
take
can
a
stay in
game
for a
for-
break.
A break.
Who wants a break? Okay, so Mary, I think I heard majority would like a break.
Yeah. How about coming back at 8:10?
All right, so now we're switching gears and going to talk about a little bit about water chemistry. And so temperature of the water does affect aquatic organisms. So I've used, you typically hear fish or aquatic organisms. I mean, if it's not warm-blooded, then you hear the term cold-blooded. And then there's a term that polychiothermic is a term that we use in college, which just basically means cold-blooded. But I think a more acceptable term for y'all as master naturalists would be ectotherms, meaning that means the same thing. They get that their body temperature is derived from externally, right? Versus an endotherm, which would be warm-blooded, where we can control our body temperature. So anyway, just those might be two new terms for y'all, but ectothermic and endothermic. So what does water temperature affect? Well, it can affect metabolism, feeding, reproduction, behavior, and then here in Texas, our fish are warm water fishes. And what that means is that, as opposed to cold water fishes, and what that means is that they can tolerate a wide range of water temperatures, ranging from 39 degrees Fahrenheit up to 100 degrees Fahrenheit. And the implication of that is that that means fish are widespread throughout the entire state. Now, warm water fish grow the best in a temperature range of 74 degrees to 85 degrees. So if you were to they do stock rainbow trout. Heck, I think they even stock them in Resolve Park. They're cold water fish. They require a higher water temperature. Those fish are not going to thrive in our warm water, in our warm Texas water. They just won't, and they won't reproduce. They do stock them below some of these lakes where the water coming out from the bottom of the lake through the spillway is, at that 39 degrees that those rainbow trout like. They like that cold water, but by and large, they're considered cold water fish. So that's temperature, and because these fishes, their body temperatures are the same as the surrounding water or environment, that does play a huge factor in how they make their living. Looking at turbidity is another way of saying the water is cloudy or visibility is reduced. So pure water is clear, colorless and odorless liquid. Turbidity happens when water becomes cloudy, and that can be from biological, or it can be from other causes. Could be from sediment, suspended clay. But turbidity, let's see, I already said it, from clay, which can come from erosion, or it can be from an algae bloom. And I think you're going to see that when you go out to Resolve Park. When the algae blooms happen from an overabundance of nutrients that have come into the system, those microscopic plants, when a system's in balance, the nutrients are in balance as well. But when you get an input of excess nutrients into an aquatic system, then that spurs primary productivity, and those algae just go crazy. The image in the photo, the image has a Secchi disc, and this is a device that we use to measure relative clarity or turbidity in an aquatic system. And the way you use that is it's tied to a rope, and the rope has graduations on it, and you lower it down into the water until the white field disappears. And then you raise it up slightly until the white field reappears. And then you note the depth on the line at which that happens. And then you'd record that. So measuring turbidity with a Secchi disc one time is not going to give you a lot of information, but measuring turbidity with the Secchi disc once a week or twice a week or what have you would be a better way to make predictions about that aquatic system. Let's see. So a reading of 18 to 24 inches is considered sufficient clarity for phytoplankton growth, because sunlight has to penetrate. And it also is sufficient for predators that rely on sight to feed. So it allows enough clarity for predators to see their prey. In an aquatic system, primary or productivity is tied to the amount of carbon that's fixed. Fixed carbon unit is fixed. Carbon is essential for life because it's the fuel that living things need. So if you look at the byproduct of the sugar or the starch produced from photosynthesis, it's C6H12O6, right? So that's glucose. That's the formula for glucose, and the C being carbon. So when plants photosynthesize, they're making starches or simple sugars. And so they're actually cleaving the carbon off the carbon dioxide as part of that reaction. I should include the photosynthetic form diagram in here. I have that in another presentation. Maybe I need to add that. But anyway, looking at pH. pH is also very critical in an aquatic system, because pH, a lot of species live in a narrow range of pH. So we all know, or should know, that pH is measured, it's a logarithmic scale. It's measured from 0 to 14. 7 is considered neutral. pH measures the acidity, which is the hydrogen ions, and also alkalinity, which are the hydroxide ions of water. When you have a neutral pH of 7, it means the hydrogen ions to the hydrogen oxide ions are balanced, and therefore it's neutral. When you have pHs above 7, it's basic. When you have pHs below 7, it's acidic. So fresh water generally has a pH range of 6 to 10. pH does change over a day due to respiration and photosynthesis. So at night, when there's more carbon dioxide in the water, because living things are respiring or producing it, pH levels, that carbon dioxide in the water combines with water to form carbonic acid, which is a weak acid. And so it lowers the pH. During the day, though, pH increases because phytoplankton are removing carbon dioxide from the water during photosynthesis, and then that can actually cause the pH to increase. And so if we look at our scale, you know, stomach acid is a pH of 1, and then you get to drain cleaner, and that can be a pH of 14. And then pure water, distilled water or pure water is considered to be 7, which is the standard. So fish are going to be able to live in a range from 6 to 10. So in this range. The mineral composition of the sediment does impact it. So in Texas, the further east you go, well, just not Texas, in the United States, the further east you go, there's less limestone or calcium carbonate. And so therefore the water tends to be more acidic. Plus you get a lot more forested areas where they're dropping leaves into those streams or lakes or ponds, and then that can have a net effect of lowering, causing the pH to go, you know, lower outside of that 6 range, for instance. And so maybe fish, you may not have the same fish composition in the eastern part of the United States versus, say, Texas or a state where you have hard water, for instance, that's buffered, because that's what calcium carbonate does. It buffers the water and it prevents wide swings in pH. So it makes it the system more stable. Oxygen is probably the number one factor, the number one factor that affects all aquatic organisms, living aquatic organisms. And the oxygen in the water comes from diffusion from the air and also from photosynthesis from aquatic plants. Not only the algae, but it can be macrophytes as well. Macrophytes being some of the higher plants like the submerged plants that are rooted to the bottom. As they photosynthesize, they're releasing oxygen into the water. You can get some oxygen diffusion from wave action. So when the wind's blowing across the surface of the water, it creates waves, and some of that oxygen in the air will slowly diffuse into the upper levels of the water. But by and large, the most of the oxygen comes from photosynthesis, in that in that layer of water that's very productive where you have algae production. Because our atmosphere is 20% oxygen, or if you were to measure it in parts per million, that would be 200,000 parts per million. So when you're looking at aquatic systems, the amount of oxygen, we measure it in parts per million, right? So dissolved oxygen levels rarely exceed 10 parts per million in water, although it does go back to how much photosynthesis is going on in the system. However, 7 parts per million is more common in an aquatic system. And so those organisms are very well adapted. And also cooler water is going to hold more oxygen. So in flowing water, where it's flowing over rocks and there's a lot of turbulence and the water's cooler, then you tend to get some of these animals that really can't tolerate lower oxygen levels because they've adapted to live at a higher oxygen level in those moving streams. But when you get down into the coastal plain where the water's moving more slowly and the water's a lot warmer, those fish tend to adapt to maybe lower oxygen levels. But by and large, when oxygen concentrations dip below 3 parts per million, that begins to stress most of our warm water fishes. And then when you get down to levels below 2 parts per million for an extended period of time, and it doesn't have to be that long, could be an hour or two, that will kill many many of the larger aquatic species, like primarily fish. Let's see.
John?
Yes.
This is Lisa. What affects the parts per million? Is it, I mean, I was trying to follow everything, but I'm also looking at the charts and not, can't listen and write at the same time and look at it. What would impact the parts per million? Like, I guess like big floods and stuff, you'd have a lot of particles in the water, but what kinds of particles are you talking about, and what makes it be more or less?
Okay, so if you have a lot of photosynthesis going on, which would come from the phytoplankton, so typically, if you the maximum amount of oxygen, atmospheric oxygen, that will dissolve in water is about 7.8 parts per million. And that is driven by temperature and pH. I mean, temperature and salinity. The higher the salinity, the salts actually do not allow that much oxygen to dissolve in the water. Wow. But when you add photosynthesis on top, then I've seen oxygen levels in water be as high as 14 parts per million. And that's right at the surface. So when you have a lot of algae producing oxygen through photosynthesis, you'll see higher oxygen levels. Now, what can cause lower oxygen levels? There's something called biological oxygen demand. And so if a system's overloaded, and when I say system, let's take an example, a small impoundment, then when the sun goes down and photosynthesis ceases, everything continues to respire. Mm. And the net effect of that, and that includes bacteria, that includes the invertebrates because they're extracting oxygen from the water. That includes plants. Plants actually go into the dark cycle in reverse. So they actually extract oxygen out of the water as well. Then you have your higher forms of aquatic organisms, the fishes, and depending on how many fish you have, and also weather conditions, right? So if you don't have a wind, then there's no photosynthesis, and literally there's diagrams that show a curve of how oxygen dips over from evening into the early morning, and then as soon as the sun rises and photosynthesis begins again, those oxygen levels climb back up.
So that
So it's basically due from biological factors.
So the 3 to 5 parts per million, that 12 to 24-hour tolerance, is that just for a certain like subcategory of species that can only tolerate, like the range of tolerance for stressful conditions? Does that equal the demise of the organism, or is just what does that mean exactly?
Well, I mean, if it sustains itself, yes, the organism is stressed, and as all living things that become stressed, it lowers their ability to fight off infection, for instance.
Okay.
And so yeah, if it's for an extended period of time, it can cause that animal's demise to die, or it could even make it more susceptible to predation, right? Because it might be at the surface. I mean, when fish are oxygen stressed, they will come to the surface and try to gasp atmospheric oxygen.
Okay.
I mean, it's typically for catfish. We see that, but I think a lot of fish will get up right near the surface, and if it's really bad, they'll jump out. They'll jump out of the pond or lake. So, but then you hit that threshold below the 3 parts per million, and typically, and now I'm speaking from the standpoint of fish that were held in captivity or in ponds that you can actually observe. They and because I deal with farm ponds quite a bit in my profession, I'll get people that call me that they had a low oxygen episode, and there'll be a 2 or 3 day delay before those fish begin to float.
Oh no.
But typically they'll think it's due to a chemical, or they'll blame it on something other than oxygen. But by and large, if it's big fish that have died, mostly the big fish that have died, then it's pretty much a clear sign that that's oxygen, because they have kind of a higher oxygen demand than smaller fish.
That makes sense. Thank you.
You're welcome. Let's see. So another cycle that y'all need to be aware about is the nitrogen cycles. About 70% of our atmosphere is nitrogen. And of course, nitrogen is a large component of protein, of our amino acids. And so in the nitrogen cycle, N2 is atmospheric nitrogen. But in an aquatic system, the nitrogen can come from decomposition of detritus, or plant matter decomposing. Also, fish excrete ammonia through their gills. They have specialized cells called chloride cells, where they can uptake salts or excrete salts, but they also excrete ammonia as a waste product through their gills, through the chloride cells. And ammonia is highly toxic, as we all know, or should know. But fortunately for us, there's bacteria that exist in the air, soil, and water. And those bacteria are chemotrophs, so they actually will reduce the ammonia to nitrate, which is a less toxic form, and then it gets reduced further to nitrite, and then eventually through denitrification that it goes back into the atmosphere as nitrogen gas. So it's not only excretion of excreting metabolic waste through the gills or through the digestive tract or through the urine. It's also when animals decompose and release that nitrogen into the system. But that's all mitigated by bacteria, 2 different types of bacteria. And so they're very important to all life on the planet because that's what recycles the nitrogen through the environment. I could talk about carbon cycles, phosphorus cycles, but that's probably way beyond what we need to discuss for this particular chapter. But let's talk about some of the threats to our aquatic systems. And it should not be a surprise that human activities are the primary threat, right? So humans have the ability to change their environment, and we do that readily. And sometimes there's unintended consequences, such as, cutting off spawning salmon from reaching their home stream to where they can reproduce and lay eggs and die, all the way to channelizing rivers, leveeing them, where you're cutting off sediment flow out to the marshes, starving the salt marsh, and where it's eroding away. So, I mean, these are all things. Also, because we have global transportation, we are importing, we're spreading invasive and nuisance species throughout the globe. It's kind of interesting, right? That smooth cordgrass, Spartina latiflora, which is the dominant vegetation or grass in our coastal marshes. It's been introduced to Seattle up in the Puget Sound, where it's considered an invasive and a nuisance species. So something that is out of place, something that's native in one part of the country, but translocated to another part of the country, then creates a huge problem for that new location. And we see that all over, right? So we'll talk about some of those. Point, non-point source, or non-point source pollution, I've already said it's something like 78% of all the pollution we can measure. Those include the fertilizers that come off the lawn. I know people want to point the finger at farmers, but everyone's guilty, right? But primarily the reason, hopefully, you have some farmers that want to stay in business, but because fertilizers are not cheap, nor are pesticides, farmers tend to hopefully be better educated about using them wisely. But the residential homeowner that can walk into any big box store and buy, I guess it's a good thing. I've seen them reduce the size of the fertilizer bag from 50 pounds to 25 pounds, because 50 pounds is way too much. But you should really only be fertilizing your lawn twice a year. Some people fertilize it once a month or more often. They put it out at the wrong time. right before rainfall because they don't want to get out there and water it in, or don't want to use their water and have to pay for it. There's a whole variety of reasons. But nevertheless, there's an overabundance of nutrients entering our aquatic systems, which impact it. Pesticides, people don't bother to read the label and apply pesticides properly. They just put it out at will. And so it's showing up in our drinking water analysis. Same thing with household chemicals. People, they do have the household chemical collection days. Some places like the Dolores, Fenwick area, you can drop off chemicals and recyclables, I believe, all the time now. But down here, they have these specialized collection days, right? Where you take all your old stuff, your chemicals to get rid of them. But some people don't do that. They dispose of them either down the drain, down the toilet. Sewage treatment plants do not remove pesticides from they're only trying to remove nutrients and the solids, but they do not do typically anything else that's put down the drain, like household chemicals or pesticides or whatever. And then we have siltation, which can impact siltation from land runoff. So when they're doing construction sites, they put up silt fences to try to keep the sediment from washing into our aquatic systems. That's more of a factor where you have fish that are more adapted to cooler water, because the siltation can cause thermal pollution. So it's in the water. You have a bunch of silt in the water. The sun heats up the silt. It changes the temperature of the water. And if you have cold water fish, like our rainbow trout, for instance, then they can't tolerate that. They end up dying. But siltation soil can also be a carrier for a lot of these chemicals. And that's the problem with siltation. It can carry oil, it can carry the pesticides and other things. And then we get bacteria from everything from, there's a reason that some cities have clean up after your dog ordinances. And it's because, and I didn't realize this until a while ago, not all that long ago, dogs have the highest level of fecal coliform bacteria in their poop than other warm-blooded animals. And that's why, and so when you get a bunch of dogs being walked and leaving their poop on the grass, on the lawn, on the sidewalk, on the street, wherever, then when it rains, that fecal matter gets dissolved and the bacteria just get washed down into our aquatic systems. And then you get a situation where you can get such a heavy bacterial load in that water that they have to close the beach to swimming, or it impacts recreation. So you can't use that. You can't use that body of water for swimming. You can't use it for drinking. You can't use it for fishing or what have you. Same thing with chemical contamination as well. And then I already talked about point source pollution. Those are permitted in industrial complexes where they do discharge under a permit and are monitored by regulatory authorities. So you get all these different factors. So, when they're changing flows, they either can straighten a river channel, they can levee it, they can divert the natural flow, and then of course damming a river, which we've done. and do quite readily, and probably will continue to do in this state to meet our water demands. Looking at invasive species, we have a whole slurry of them. In this picture, we have some water hyacinth, which is kind of like a good guy compared to this one. This is a giant Salvinia. It's a aquatic fern that came up from South America. It's kind of interesting how all these things seem to originate in South America. Hot water hyacinth came from South America. This has come from South America. This is in Caddo Lake. This particular plant forms floating mats or vegetative mats up to 3 or 4 feet thick that can support the weight of a full-grown man. And the net effect is that it blocks all primary productivity to that water body and suffocates the lake. So nothing can survive in that with that sort of cover on top of the surface of the water. There's no photosynthesis, and consequently everything, the entire food web collapses and dies. Zebra mussels is fairly new. When I first took my first job in Louisiana, they were talking about zebra mussels. They were in the Mississippi River drainage. They were scared. They were training us to identify zebra mussels in Louisiana, how to recognize them. These are biofoullers. They just grow on top of each other. They have the net effect of clogging pipes. So in industrial complexes where they use water for cooling the processes, or even water systems for freshwater delivery or purification, these zebra mussels can move in. And if you think about seeing images of cholesterol blocking an artery, that's exactly what zebra mussels will do. They're filter feeders, but they're biofoulers, and so they can close down a plant by restricting the water flow through their piping system. So consequently, they have to stop the industrial processes. They got to dismantle the entire system, clean out those pipes, and then restart the plant. But they are now in Texas. I think it took them a while to get to Louisiana, and I don't know if they've become such a problem there that they were anticipating, although they have quite a bit of petrochemical industry in Louisiana, as we do here in Texas. But it's been almost 23 years, and they finally have reached Texas. They first entered Lake Texoma. They're now in the Brazos River Basin, and they were in Lake Belton. I'm trying to think, they're even further south at this point. So it'll be interesting to see, because we have all the petrochemical plants in the Freeport area, and the zebra mussels are going to be in the Brazos River drainage. And so it'll be interesting to see how that pans out. But they are here in Texas now, and primarily transported by boaters that are moving their boats from one lake, an infected lake, to an uninfected lake without taking the time to wash or inspect their trailer or live wells or what have you for those mussels. And so they spread them that way. And of course they spread through the drainage as well. And then this picture here is our channeled apple snail, which you'll become acquainted with if you're not already when you go out to Resoff Park, because they're all over there. They're all over Brazoria County. And they're kind of an interesting animal. They get as big as a baseball. And I guess something eats them. because I find the shells up on the shoreline of them. But the female will lay her eggs on vegetation that's standing out of the water, or in this case, this picture, a rock. And then the young snails, once they hatch, they then crawl back into the water. So if these eggs were flooded for an extended period of time, they wouldn't survive. Point, non-point source pollution. I talked about the hypoxic zone. In the media, you'll hear it referred to as the dead zone, but hypoxia means low oxygen. And it's all driven by nutrients flowing down the Mississippi River drainage out into the Gulf of Mexico, where it causes phytoplankton to bloom. And then that phytoplankton then dies and sinks to the bottom. And then with that decomposition going on, the critters that can't swim, the ones that are in the mud, the benthic organisms like the worms and the clams and the snails, they end up succumbing to the low oxygen levels. And if we look at our diagram here, the red is oxygen levels below 2. So it actually sets up with stratification, because the Gulf of Mexico does stratify, and a good tropical storm or hurricane will stir this up. But this system sets up during the summertime. And you can see that, you know, initially when they first documented it, it was from the Mississippi River drainage, or the effluent of the Mississippi River, over to about here, and it is slowly expanding. So now it's actually, they're finding it over across in Texas waters. But it happens in about 160 to 200 feet of water, and it does stratify. The Gulf of Mexico does stratify, and it literally takes a storm system to destratify and stir that water up and reoxygenate that area of the Gulf of Mexico. But that's all from nutrients that are being inputted. And then if we look at our map over here globally, well, these red dots are representative of hypoxic zones. And you can see that they're all around North America, South America, Europe, pretty much every continent except for the Antarctica and the Arctic are affected by low oxygen levels, and primarily due from nutrient input from the land. And that's it. I have one last slide. That's have any questions, and we'll, if you don't have any questions, we'll wrap up.
This is a very interesting talk that you gave. It's very interesting. You want to look into it more.
Well, if you'll take a look at chapter 18 that deals with this in your curriculum, we'll talk a lot about the lentic and lotic systems. One thing I failed to mention with the rivers, with lakes, that productivity is internal. So the nutrients come from within the system. With a river or a stream or creek, the primary drivers of that system, the energy, besides photosynthesis, the sun's energy, but the nutrients come from outside the system. So from runoff, if you will. And also those systems are driven a lot by detritus. Here again, that's organic matter that is eaten by some of the majority of the invertebrates. And that's what drives those systems. So But yeah, I would encourage you to take a look at 18 if you have, and then if you have further questions, you got to get hold of me.
Thank you.
You're welcome. Thank y'all.
Thank you, John.
You're welcome.